Assalamualaikum, bismillahirrahmanirrahim. Yes, hello everyone. So today we are going to be talking about solving chapter number 4. We had finished from chapter number 4 about flow of a liquid through a tank or a pipe. There is a leak, and we also have studied flow of a gas within a pipe or in a tank. And if we have a liquid pool, what is the vaporization rate? So that was the topics. These were the topics that we had taken. So we are going to continue. We solve from 4.1, 4.8. So you can go back to my video. Here we are going to continue solving 4.9. So what do we have? We have a 31.5% hydrochloric acid solution. It's pumped from one storage tank to another. So it's like two storage tanks, and we are trying to pumping it from one place to another. The power input to the pump is 2 kilowatts. So I have the shaft or the work is equal to 2 kilowatts, and it's 50% efficient. In this case, we are talking about a 50% efficient of 2 kilowatts. That means it gives us only 1 kilowatt, which is 50% multiplied by 2. Okay, what else? The pipe is plastic PVC pipe with internal diameter 50 millimeters. If we know PVC pipe, we can identify the K1 and K infinity for the friction factor. At a certain time, the liquid level in the first tank is 4.1 meter. So the pipe that leaves the first tank is about 4.1 meter, right, above the pipe outlet. Because of the accident, the pipe is severed between the pump and the second tank at a point 2.1 meter below the pipe outlet. Okay, so now we have above the pipe outlet, we have the liquid level, which is 4.1 meter. The second pipe is 2.1 meter below the pipe outlet. This point is 27 meter between the two tanks. Now we want to calculate the flow rate in kilograms per second, which is Qm, okay, or the m dot. We have the viscosity and the density information to calculate the Reynolds number so that we can use it for the friction factor. Okay, so what do we have? So if we have the system here, so we have 9, and we just need to get an idea about how does that look like. So so it's like we have a pipe outlet from here, and this pipe outlet that gets out from here, it goes to a pump, and then it goes to another tank which is lower. Okay, it goes to another tank which is lower, and in this case this is like this is about 2.1 meter less. So here we're talking about 4.1 meter. So let me write that, and that is 4.1 meter. And here I'm talking about it is at lower than the pipe outlet by 2.1 meter. And the distance we have between the two tanks is 27 meters. It's always important to understand the whole details because with the details you can understand what can you do. And where we are trying to do our mechanical engineering balance, you're trying to do it from this point till this point here. Okay, great. So we are going to, of course, start with the mechanical energy balance. And as we know that you're thinking of m dot, and the mechanical energy balance is this equation. If you go back to equation 428, so that is delta P, as it's you're talking about liquid, so we will not write dP over rho. It's delta P over rho plus delta U square 2 alpha GC plus G over GC into delta Z plus F is equal to minus W over M. Okay, great. So we need to look at our assumptions, what we can take forward from here. What I would say that now delta P actually is not equal to 0. We can say about is equal to 0 because it's not pressurized. It is not pressurized, because if it is pressurized, we guess that this could be big, but it could be negligible in that sense. Okay, so we'll consider that delta P is not pressurized, so it's going to be 0. And number 2 that we are going to take as an assumption here is about alpha is equal to 1, where we are considering as it is as turbulent flow. Why? Because you have a pump. Actually, it's not that It's not that accurate. You need to calculate it. But because you have a pump, I'm going to consider that as turbulent flow, and alpha is equal to 1, just to make things easier. Okay, now what information do we have? Okay, so these are like my assumptions. Okay, what information do I have? I have that, well, delta z, I can see from delta z here that I have there's a distance of 2.1 meter down here from this point, and the distance is 4.1 meter from this point. So from point 1 to 2 I have 4.1 plus 2.1, right? So in this case my delta z is equal to 2.1 plus 4. I'm going to start writing with the white. So delta z is equal to 2.1 plus 4.1, which is equal to 6.1 meters. What else do we have? We have the W, which is 2 kilowatts. And if you multiply this by 50%, you're going to get it as 1 kilowatt. And if you want to change that into joules, this would be like 1000 joules, okay? 1000 joules. Great. What else do we have? Okay, we have let's look at our problem here. So we have now that we have this. Okay, we need the m to find m. What about delta u? Okay, we also have a problem with that thing here. Okay, the friction factor. Friction factor. Okay, we need to do something about friction factor, but friction factor will be a function of maybe Reynolds number and u. Okay, both of these. That will be dropping to 0. Okay, so most probably now let's calculate now m, and then we're going to look at f. Okay, m and then f. So for m is equal to, if you can just recall, it's like talking about the u into a, which is the volumetric flow rate, multiplied by the density, which is the mass flow rate. Okay, I just wanted to put the dot. Okay, so this will be equal to 1600 kilogram per meter cube, which is given to us, into u, and area is pi d square over 4. So pi d square, we already have this information, divided by 4, and that will be about 3.14 u2. Okay, so we have a 3.14 u2, right? So it is a function of the velocity here. What else? Let's look at f now. We said after m dot we want to look at f. So for f, remember that f is kf, right? Into u square over 2gc. And in this case, kf that we have here for the friction, we have for the entrance, plus the pipe, which is 27 meters, right? Plus the k exit is exiting that pipe. And if you just substitute these numbers here, k entrance, okay, so k entrance, if you want to go back to the equations, like this is equation 439, I'll write that in blue. Okay, so equation 439, I have my k entrance is equal to 160. I have the k1 and k infinity, right? 160 over Reynolds number plus 0.5, and my k exit is equal to 1. And then if I go to find k exit now, for the k pipe, I found k entrance and k exit. So for the k pipe, okay, this is equal to 4FL over D. Oh no, how to find f? Okay, then it will be a function of f in this case. So for f, 27, this is the length, over d, which is 0.05 meters. So we have 2160f, okay? So in this case, if I substitute just to put my f term, so my f term now is equal to 1.5 plus 160 over Reynolds number plus 2160f multiplied by u square over gc. So you can see here in my problem, it's like my f is a function of f and u, and my m dot, the m dot I have is a function of u, and I already have in the equation of the mechanical energy balance also this u here. So it's a function of F, U, Reynolds number, and all that. And here what we need to do some kind of an assumption so that we can get our process correctly. Just returning to the mechanical energy balance and substitute. So to do this, so what do we have? My equation now is delta P was 0, so plus U square over 2 U square, because we said it's delta U square, right? But we are considering like the output is from the pump, which is high velocity in comparison to the input, which is 0.1 at the level of the tank. So if you just go down here, so the point here, you're considering the U1, and here we're having U2, and U1 is nothing. It's like in comparison to U2. We are saying U2 minus U1 is equal to U2. Okay, so going back to that, so delta U2 square will be U2 square. Okay, U2 square plus, or it was not a G over GC, if you can remember, right? Since you're talking about SI units, so it's just G, no correction factor. And this is the F term. Okay, that is the F term that I have here. So that's the KF into U square over 2. And that is equal to, if you can remember, the W which was 1000 joules over the mass flow rate, which is 3.142. So now with this equation, what you're going to do with this equation? So the procedure starts like that, okay? So what is the procedure? The procedure starts that first what you need to do, you need to assume U2, all right? You need to assume or guess. I would say guess rather than assume. Okay, so you're going to guess U2. And from the guess of U2, you're going to get the Reynolds number. And if you get the Reynolds number, then you're going to use figure 4.7, so that you have the Reynolds number and the E over D, so that you can find the value of F. Okay, so in this case, you're going to find, you're going to find the value of F. So now I found the value of Reynolds number and F, and I already guessed U2, right? So these are the values. This is the Reynolds number, this is U2, and this is F. And now what I need to correct, I just need to check if my right hand side is equal to my left hand side, right? So this is what I need to do. If it's not, then I need to compare U2, of course, with my, it's like I can't calculate U2. I can't consider U2 is just an unknown, right? It's like an unknown here. And it's like an unknown in this equation. And after you find U2, actually, you can compare U2, the new 2 that you obtained, minus the U2 of the guess value, and that is approximately 0 or not, right? And then you're going to do your iterations. Based on that, you're going to do your iterations. The maximum, if you want to go, it goes like 3, let me say 3 iterations now, and within 3 iterations you're going to get to a good value there. And if you just want to know the answer after you do the whole job of this system, you're going to see that the discharge velocity will be 4.835 meters per second, and that was the meters per second. If you now you just can calculate the mass flow rate, which was equal to rho U A. If you remember, it was 3.14 U2, so you're going to multiply 3.14 to U2 to get 15.18 meter cube per second. And of course you can now multiply this by the density, and the density was about, so that is not m dot. Okay, oh no, that's directly m dot. I already have it. Oh, I already have it. So that will be kilograms per second. So 15.18 kilograms per second. So that is the solution of what we were searching for, and this was the way how we calculate the mass flow rate if we had a leak between these 2 points. Okay, great. So now let's go to 4.10. 4.10. Okay, so what does 4.10 tell us? 4.10, the morning inspection of the tank farm finds a leak in the turpentine tank. The leak is repaired. Okay, so we repaired it. An investigation finds that the leak was 0.1 inch in diameter and 7 feet above the tank bottom. Okay, so 7 feet above the leak is the HL. Records show that the turpentine level in the tank was 17.3 feet before the leak occurred. So it went down from 17.3 feet, and because of the leak, it went down to 7 feet. Is that right? No, that's above the tank bottom. Okay, it was 17.3 feet before the leak occurred and 13 feet after the leak was repaired. So it went down about 3.7. No, sorry, that's 4.3. About 4.3 feet. The tank diameter is 15 feet. Okay, so determine the total amount of turpentine spilled. We can know the amount. It's not that difficult, by the way, because if we know the difference between these 2 feet, and if we know the difference between these 2 feet, and we already know the area, we can calculate how much amount. However, what is the maximum spill rate? What was the spill rate? Well, the spill rate is the amount that had been down within a certain time, right? And the total time the leak was active. Okay, that's a good question as well. The total time the leak was active. We can calculate this as well. The density of turpentine is given to us. Okay, so what do we have? We have 410. Let's start with 410. So I have 410 here, and in 410 we need to look at our figure. So our figure looks like that. Let me draw this. So what do we have? So it was about, let me make it longer. Okay, so it was about 17 feet, I would say 17.3 feet. 17.3 feet, but because of a leak that we had here, coming out, it went down to 13 feet. So that was 13 feet. Okay, now what was the amount that had been that went down? So this is the amount that went down. What is the diameter? The diameter of this thing here is 15 feet. Okay, so we can say like pi d square over 4. We can get how much is the amount of the area. That's the area, right? If you multiply it by 4.3 feet, you're going to get the volume of this area here. You're going to get the volume, and this volume is going to be important information because it tells you how much had been spilled. Okay, so in this case, I'm already starting solving, but I'm just trying to put all my information here. What else do I have? I just have here, it says 0.1 inch leak. Okay, that the hole is about 0.1 inch in diameter leak. What else do we have? What is the distance of this hole? I mean, how high it was. I forgot how high it was, so I don't know if it was mentioned or not. Investigation 0.1 inch and 7 feet above the tank. Okay, so said that it is 7 feet. Okay, so here that is 7. Okay, so I have 7 feet here, 7 feet above the tank. The leak is above the bottom of the tank. Okay, great. So let's solve it. We want to know how much amount had really been spilled out, and to know how much amount had been spilled out. So the V spill, I would say, is equal to like V1 minus V2. I already mentioned this. So I'm just mentioning the pi d square over 4 into the difference in the height, right? So the difference in the height, telling you what is the volume of that amount that had been spilled. And in this case, I'm going to have pi multiplied by 15 feet square, which is the diameter, into the difference in the height, which was 17.3 minus 13 feet. and that the answer will be about 759 feet cube. Okay, if you want that in gallons, this is about 5680 gallons. Okay, so this is the amount that I have in feet cube that have been spilled out. Okay, so what do we have? We have the flow of a liquid, right, through a tank. Flow of a liquid through a tank, and based on that, like if you have like a flow of a liquid leaking from a tank, you're going to use the equation, and that equation that you're going to use is that, which is Qm is equal to rho A C naught multiplied by 2 GC PG over rho plus GHL. Great. So what do we have here? C naught, I'm going to assume C naught is equal to 0.61 for sharp edge, and I'm going to consider that as sharp edge. We already have the value of area, right? The value of area here, which is pi d squared over 4, but not to confuse, like here I'm talking about the area of the hole, right? I want to calculate the mass flow rate that comes out of the hole. So that is pi 0.1, okay, 0.1, that's the whole, 0.1 square. Oh, 0.1 is an inch. Okay, so that's 0.1 square. Then I need to, of course, to have this in feet, so that will be about 12 square for 1 feet square. Okay, so that is for A. We already have the value of the density. So what else do we need? We have HL, by the way, right? We have HL. Before getting to HL, let me see what's PG. So what's PG, right? Did you think about it? What's PG? It's open to the atmosphere. Open to the atmosphere. So in this case, PG is equal to 0. Okay, that makes our life easier. So PG is equal to 0. What else? I found everything. I found everything what I need. What is HL? HL actually says the initial liquid height above the hole. And what was the initial liquid height above the hole? What is the height above the hole? So here's the hole that I have here. And the liquid height above the hole was here at the beginning. Okay, again, so this was the hole, and the liquid height above the hole, which means it's like I'm looking at what pressure like I have. It's not like pressure, I'm doing the mechanical engineering balance between this point here and this point there. So from this distance to that distance, we have 17.3. That's from here till here, minus the 7 feet that I have here. So 17.3 minus the 7 feet to get this here. Okay, great. So what do we have obtained now here? We said that is equal to 17.3 minus 7, which is 10.3 feet. Okay, great. So can we substitute now? Yes, we can substitute. Let's go on. What I need to do is to substitute all the numbers. So rho multiplied by area, which is 5.45 into 10 to the power minus 5 feet square, into C naught 0.61 into the square root of 2 of GC multiplied by the HL, which is 10.3 feet. Okay, 10.3 feet. If you do this and you multiply it, the answer will be about 0.047 pound mass per second, and that will be about 169 pounds per hour. Pound mass per hour. Okay, great. So what do I have here? Actually, I have calculated all of what I need, and I can consider the equation. Now, that is the first part. Let me concentrate. So that was the first part. So it asked me in this first part to find the total amount of turpentine spilled. Okay, so I have the total amount. Did I find the total amount? Actually, what I found here is what was the rate. The total amount was the volume that I obtained, which is V spill, and you just multiply that by density to get the total amount. Okay, so I think you got it, right? So I have the total amount spilled, I have the maximum spill rate, and what about the total time the leak was active? Okay, the leak was active. We already have TE, the time that for the whole thing to leave the system. But actually there could be an easier way of calculating this. So I could consider the equation for the time. I don't know if you recall the equation where we had the HL. This is part C, by the way. So HL is equal to HN naught into C naught over A over AT into 2G HL naught into T plus G over 2, I think so. I need to look at that equation. G over I need to just check. So that's a C naught into I forgot. Okay, just hold on. Let's look at the equation for a moment. So that was the place that we were in. That was for gases. So let's go for the one for the liquid. Okay, that's for the friction factor. I think we already arrived. Okay, great. So what do we have here? Our equation, that is our equation here. So that's G over 2. So that's the equation that I have here. And this is multiplied by 8 over AT multiplied by T. So G over 2, A over AT multiplied by T. And this is square, and that is square. So that is the equation that I have here. Okay. Again, what is HL? Solving for HL, the liquid level in the tank heats that. So if I have HL and HL naught, I have all the other values. I have PG is equal to 0. So I can calculate the T time here. I can calculate the T time. So it's as simple as that. It's as simple as that. It's only an equation that you're going to substitute. Okay, so these are the values that I have for HL and HL naught. Okay, it came from where? It came from this equation that we started with, the mechanical energy balance, and we substituted for the velocity. You consider C naught, and then we said it's easy to take a rule of thumb for C naught. And then we substituted, we got that equation here, but we know that the tank empties, right? It takes time to empty. And because it empties, we are going to have the height is decreasing and the velocity mass flow rate will also be decreasing. And because of that, we substituted the differential term, which is change with time, and putting it change with time, we arrived to that point. And we integrated just to solve for dm by dt and then dhl by dt, which is part of dm by dt. We took that from HL naught to HL. So it changed from HL naught to HL. And we obtained that equation here. So I hope that you got the idea, right? You got the idea. So it changed from HL naught to HL. So what was HL naught and HL? So that was the integration limits, right? And HL or HL naught is above the leak hole. So what I have here, what do I have here is that, let me look at the red part. So talking about HL naught to HL, well, sorry. So I'm talking about here, it was 17.3 feet. 17.3 feet minus 7, which was the first part. And we already said that this is 10.3 feet. And the second one, so this, I would consider this as HL naught. And HL was 13 feet minus 7. 13 feet minus 7. This is minus 7. 13 feet minus 7 is equal to 6 feet. Okay. So that is HL naught and HL. All what I need to do is now to do the substitution here. Okay, to do my substitution, which is 6 is equal to 10.3 minus 0.61 into 5.45 into 10 to the power minus 5 feet square over the area of the tank, which is AT. Okay, 176.6. And that is multiplied, that is plus, let me multiply before the 2GL, 2G L naught, right? That is L naught. So that is 10.3 feet. And then you're going to continue plus G over 2 plus G over 2 into C naught into A, which is 5.45. I know that is a lot of writing here. Over 176.6 and then multiply by T, right? Square. So if you're going to solve for this, you're going to find that T is going to be two values, and the first value is about 281 hours, and this, which is about 11.7 days, and the other one is about 2082 hours. And of course this doesn't make sense, so this is the correct one. So it's about 281 hours. Actually, you could also talk about, well, if I have a leak here, right? If I have a leak here getting out, and I already know the amount. I already know the amount that had one down. I have the QM. If I have the amount, I have the QM. Can I relate this to this? That is more or less, it will give you a close answer towards that, because this is like a kilogram per second. And this is the amount in kilograms that I can obtain, so I can get an answer there. Okay, so just to look at it, if you can recall the mass spilled, I'm just taking this like another way of solution, okay, which is like an approximated way. So M spilled. I said approximated because there's a kind of energy, mechanical energy that you need to go through, rather than saying you're just eliminating all the other effects of PG or the other effects that's getting out as a velocity here, the friction factor. So sometimes there are some kind of assumptions that make things life easier. So I'm going to make it easier now. So the M spilled, what was the M spilled? If you can recall, it was V spilled into the density, right? And the V spilled that we had calculated was 759 feet cube. And if you multiply this by the density, which is 55 pound mass per feet cube, and this is going to be equal to 759. Do it through your calculator, multiply by 55, it will be 41745. Okay, 41745. So that is the amount of pound mass. That's the amount of my god, is that a number? 41745. That is a really very big amount. Oh my god. Okay, that is really a very big amount that we are talking about here. Okay, so that if that was the value of M spilled, what about QM? We already calculated QM, and the QM was about equal to 169 pound mass. I'm just getting the numbers here. Pound mass per hour. 169 pound mass per hour. Now if you do your calculation, and you say just the QM, the M spilled, which is just an approximation, okay, over QM, I'm going to have the answer to be about 247 hours. I know that 274 hours is not an exact, okay? It's not an exact number. It's not an exact number to that way that we have calculated, which is 281, okay? But that was close enough. It gives us an indication that what was the amount of hours that we are having here, and we left it for 247 hours to fix it. Of course, if you look at the amount that had been spilled, that is a crazy amount. But if you look at the number of hours, oh my god, 247 hours, that is also a big... You're talking about not 24 hours, you're talking about 10 days or 11 days, right? So it took this much time to fix and because of that time that had been fixed, we are losing this much of amount. So I would consider that 247 hours is a good approximation to the answer that we have, where we can say this is the active time. The active time, because it's asked us about the active time, and the active time is the exact time that had been left. That is the time that we have lost all of that amount. Great, so that was 410. That was a good question. We liked it. And I think so the next step that you're going to do now here is to solve the next problem. So 411, that's 411. Compute the pressure in the pipe at the location shown in figure 419. That is figure 419. The flow rate through the pipe is 10,000 liters per hour. So it enters here at 10,000 liters per hour. The pipe is new commercial steel pipe, so we know the type, so we know the internal diameter. We can get this from the table. It already gave us the internal diameter, 50 millimeters. The liquid in the pipe is crude oil with a density of 928 and viscosity of 0.04 kilogram per meter per second. The tank is vented to the atmosphere. That is important to say that there's no pressure here, right? If it's talking about the gauge pressure. Okay, great. So this is the amount, and we can see here that we have a leak that occurs at that side here, which is about like 3 meters. If you look at here, the 3 meters from here. This is not a flange, okay? Just to tell you, this is not a flange. This is just to show you that, to show you the distances that we have. So what do we have as well? We have an elbow here. We have another elbow here. So we have a friction of an entrance, exit, and 2 elbows. So we have a friction of entrance, exit, and 2 elbows. So that is part of the F. So we need the Reynolds number. We need the roughness factor of the steel, and we know the internal diameter. So E over D with the Reynolds number, we can get F. Of course, we're going to get the fanning factor, just part of flowing through the pipe, but we need also the friction factor of 2 elbows and the entrance and the exit. We sum up all of these K's so that we substitute to find F. So now that is for F. What about delta P? In this case, we need to calculate delta P. So continue the problem as we said about the leak. We just go ahead and try to solve it, okay? So what do we have here? We have 411, and of course the first thing that we're going to apply for our system here is to apply the mechanical engineering balance, okay? The mechanical engineering balance. And this mechanical engine energy balance, sorry for that. So it's the delta P over rho plus delta U square over 2 rho GC plus G over GC into delta Z plus F is equal to W minus W over M. Okay, great. So what do we have here? First thing that we can say here, like what about the velocity, right? It enters with the velocity here, and it exits with the velocity. If the velocity that it enters and leaves is the same, and it's liquid, right? So we cannot say that there's an expansion here and the story where it affects the velocity. So it goes in and it goes out. So for a liquid, which is an incompressible fluid, we can consider delta U is equal to 0, okay? So all of what I have said, that it's incompressible, right? U1 is approximately equal to U2, so delta U is equal to 0. So that's the first thing that I wanted to mention. What about W? We don't have any pump here that shows in this part. So we have W is equal to 0. No work. I think my life became really simple here because I dropped out this term and also dropped out that term there. So the main factors that I have is delta Z, F, and delta P. Okay. So let's go on. What do we have here? Let me look at what do we have as information. So the known information that I have, we know rho is equal to 928 kilograms per meter cube. We know that we have mu, which is 0.004 kilograms per meter second, and we also have the value of E, which is the roughness factor, which is 0.046, and that is for the commercial pipe. You can get that, the commercial steel pipe. And of course, if you divide this by the internal diameter, this will be 0.046 over 50, which is equal to 0.00092. Okay, and based on all that, you already can calculate the area. Well, why I would calculate the area? What information do I have here, right? I have 1000 liters per hour, right? So I have 1000 liters per hour, so all what I need to do is the density. I just need the density for that. So that U is very easy to get. But I need the rest. I need the area maybe if I want the velocity, okay? So I multiply by the density, I can get an idea for how much kilogram do I have per hour. But if I'm talking about the if I want the velocity, I need to divide this by the volume, by the area, and I will get the velocity. Okay, so that's clear for us. So U is equal to, just to calculate U, so we have 10 meters per cube per hour, which is the 10,000 liters. And if you divide this by the area, right, you divide it by the area. And what is the area? The area is pi d squared over 4, and pi d squared over 4, so it's like, let me do the area here first, so that it becomes easier for me. So area is equal to pi d squared over 4, which is equal to 3.14 into 50 millimeter square. And of course I need to convert this with about 1000 millimeter and 1 meter square. Wow, that's a big number, divided by 4, and that is about 1.963 into 10 to the power minus 3 meters square. Okay, so 1.963, so I need to remember this. So that is 1.963 into 10 to the power minus 3 meters square. This is meter cube, right? So what will be my answer? My answer will be 5090 meters per hour, which is odd. So I'll just change that into seconds. So that will be 1.415 meters per second. Great. So what did I get? I got U here. I got U. And if you look at, I have U. I need U for the Reynolds number because I need to get the F later, right? So this is what I need to do. So as I got U, I directly can calculate now my rho dV over mu. And if I do this, this is like 0.05 into 1.415 into 928 over 0.04, that is equal to 1.641 into 10 to the power 4. Okay, so that's the Reynolds number. Now, knowing Reynolds and knowing the E over D, right, I can get what? I can get the fanning factor. Of course, the fanning factor is going to give me the K for the pipe. But I have other K's, right? I have K entrance, I have K exit, and I have K elbow. However, I have 2 elbows, so I need to multiply that by 2. So this is what we are trying to find out. So looking at the K pipe at the beginning, looking at the K pipe, for the K pipe, we found out that the F is equal to 0.0072 from the figure. So K pipe is equal to 4FL over D, 4FL over D, and that is equal to 4 into 0.072 into L. Well, what's L here, right? What's L? Let me write the D. term, which is the diameter. What was L? If you go back, L is 1 meter, 3 meters, and another 3 meters here. So 3 plus 3 plus 1, okay? So that was the distance between the point 1 and point 2 that we are looking at, and that is equal to 4.03. Now, how about the elbow? How about the elbow? Well, K elbow is K1, right? K1 over Reynolds number plus K infinity into 1 plus 1 over the internal diameter. The internal diameter. And if you can recall, the internal diameter was 50 millimeters, I think so. Yes, it was 50 millimeters. And to put things in inch, because it says here that this internal diameter should be in inch, okay? So that was the definition of it. So 1 inch is 25.4 millimeters. And if you do your calculation, you're going to find your answer is going to be 0.652. However, we need to multiply this by 2 later because we have 2 elbows. For K exit is equal to 1. And in this case, my F is equal to 4.03 plus 2 elbows, all right, plus 2 elbows, plus the exit entrance plus 2 elbows. We already took entrance and exit, right? Oh my God, I think so. 4.03, yeah, 4.03 was for the pipe, yes, plus 2 elbows plus the exit. Here we didn't have for the entrance because we already have that it is flowing, okay? So it's like it did not enter, it was already flowing. Great. So that is the K. That is the K. And if you know that F is equal to K multiplied by U square, and that is U, we already have U. GC, and in this case it is 1 if you are talking about meters, kilogram meter per second, and that kind of a unit. So the answer will be 6.34 Newton meters per kilogram. So that is the F. What about what will be the answer now? So we if you can recall, we have delta P over rho plus F. We already have F, right, which is the before the F we have the Z term. We have the Z term, which is the G over GC delta Z plus F, right, is equal to so that was my equation, which is equal to 0, which is W over M dot. In this case, if I want to find delta P, is going to be minus F minus G over GC into delta Z. And we already found F, and we just need to substitute here. So that will be minus 6.34 minus 9.8 over 1, of course, GC if you're talking about the SI units, and delta Z is 3 meters. Is it 3 meters? Let me make sure. Yes, it's just 3 meters here. So it's a good thing to look at that, how does it look like. So it's about 3 meters. And you multiply, of course, that by rho. I forgot to say that this is multiplied by rho because this is like delta P over rho. So my delta P is going to be this multiplied by rho, and my rho is 928 kilograms per meter cube. And if you do your calculation, this will be minus 33,100 newtons per meter square, which is Pascal, which is equal to minus 4.81 psi. So that's the pressure drop, okay? So that is my pressure drop. That is my pressure drop, the delta P. The delta P. So the delta P. Okay, great. So did we get our answer? Yes. So what was the question again? It asked us that to compute the pressure in the pipe. Okay, we want to compute the pressure in the pipe here. And we already calculated the pressure where the delta P, we said because of this leak here that we have is going to be delta P. The delta P is going to be minus 4.81 psi. Great. So that was for 11. I think so I'll keep for 412 for the assignment. It's going to be a good question that you can solve as an assignment. Don't worry about now what is 417. So here in 417, it's asking us to do some kind of a question, and it's good to give you the second three, the other parts as an assignment. Okay, I'm just thinking of the assignment questions that I'm going to hand you with. Okay, so calculate the mass flux for the following tank leaks, given that the storage pressure, so I have a storage pressure, that means there's a storage that is under pressure, okay? I'm going to tell you which equation to use if you have a storage of a certain toxic material or a material that is stored under pressure, which is equal to the vapor pressure, and of course you're trying to keep it at a certain pressure where it is liquid, and then of course if it is open to a certain different pressure which exceeds the vapor pressure, you have vapor, and then you're going to have some kind of the toxic material leaving the storage. Okay, so you're losing money and it's toxic to all beings or all the organisms. Okay, so what are the toxic materials? For example, I have 4 different toxic materials. These are the pressures, heat of vaporization, where it heats up and becomes vapor, and that is the specific volume, and these are the heat capacities. So can you tell us how to calculate this? You can see how simple. These are the only information that I can calculate. How much how much is the flux, which is the kilogram per meter square, how much mass is going to be leaving my system, right? How much mass is going to be leaving my system. Okay, so that is the equation that we have here, which is the mass flow rate by combining some certain equations. So this is the equation that I have, and this equation, as you can see, if I have any storage that is under pressure and I'm having some kind of flashing, so these are the equations of flashing. And if I want to calculate the flux, that means I need to calculate Qm divided by the area, right? Qm divided by area, which is equal to the delta HV, the vaporization heat over the specific volume, into GC over T, temperature, into the heat capacity. It looks like a straightforward substitution here. So let us try the equation. I think so we are ready to do this. So 417, in 417, what do we have here? We have Qm divided by area, and is equal to delta heat of vaporization over the specific volume multiplied by Gc divided by Cp into T. And note here that you don't need that pressure information. The pressure information here is not needed, right? Is not needed. We didn't need to know what is the pressure. So we can calculate this, which is equal to, in the first case, let me see, the first case was we have propane, so this is equal to, just substitute, okay, just substitute and get the answers, and GC is 1 in case we are talking about the SI units here. You need to check this by yourself, into the T, which is 298 Kelvin. And the answer is going to be 8.51 into 10 to the power 3 kilogram per second meter square. Okay, so that's the flux. That's the flux. And I don't want to say like it's just straightforward of kind of a calculation. And from this flux, of course, you can get a lot of information. If you know the area, you can know how much is the QM. If you know the QM, you can know, of course, if you know the area of that hole, and you know QM, and you know the ventilation rate, and then you compare that from the CPPM with the threshold limit value. So there are a lot of information that you can gain out of here. So this is like just practicing you to what you need to do. So again, QM over A is equal to 1.17 into 10 to the power 6 divided by 0.127 into 1 divided by 4.49 into 10 to the power 3 into 298. And that is equal to, I have a problem with my handwriting today. Okay, that is equal to 7.96 into 10 to the power 3 kilogram per second meter square. Okay, great. So these were the first two. I think so they were straightforward. And I'll now let's go to the problem 419. Okay, so I'm skipping because I'm looking for the problems that have very typical to systems that we may have in industries, and is going to be very interesting to solve. Okay, so 419, a tank 100 feet in diameter and 20 feet tall is filled. It's a tank. It's filled with crude oil to within 2 feet of the top of the tank. Okay, so you did not fill it to 20 feet. You filled it up to 18 feet. Okay, so talking about like this is my system here. So I'm talking about 419. So my system, what do I have? I have a big tank, and this big tank is about 100. Did it say the diameter? Did it talk about 100 feet in diameter? So that's 100 feet. Wow. Okay, so what do we have? I have crude oil inside, and what do I have here is 20 feet tall. Okay, 20 feet tall, but it's filled into within 18 feet only. Okay, of course you not fill it till the head, right? If you need to drink some water, you never fill it to the head. Just kidding. Okay, one accident scenario is that a 6-inch diameter line connected to the bottom of the tank might break loose from the tank. Okay, 6-inch diameter. Allow crude oil to drain out. If we have a 13-minute emergency response time is required to stop the leak, estimate the maximum amount of crude oil. If this was my time to stop that leak, how much I'm going to lose crude oil? The tank is vented to the atmosphere and the specific gravity of crude oil is 0.9. Okay, great. So that is the question that we have. And just let me put my 6-inch here that goes out hole, my 6-inch hole where we have at the bottom. What I need to have, I have a 30 minutes emergency plan. Okay, I have 30 minutes emergency plan. With this 30 minutes will be good. I will not lose a lot of that amount. Well, let us see. Let us see if you're going to lose or not. And here you need to look at what information do we have before we decide. So we have information of time, and what else do we have? We want to calculate the QM leaked. And here, if I want to calculate QM leaked, that is not easy to calculate. I have the diameter. I have the length here. I can't calculate the volume. Actually, I can calculate this volume or in response, or the height here in response to the area here. So this big area with this area here. Okay, what else also we can get here? Do we have any information for? So here are the equations that we have for the T term, right? Here are the equations that we have for the vessel to empty. That is the equation. But as we know that if the vessel is at atmospheric pressure, so what we'll have this PG, because it's open to atmosphere. So this PG will be equal to 0. So this drops out from the term. This PG drops out from the term. Actually, many things drop out from the term. We have only square root of GL with a 2 multiplied by the GL, HL. So that is the equation that we have. So it came out to be a very simple equation. So T, the equation is equal to T is equal to the area of the tank divided by the area, okay, and that is divided by 1 over C naught G, okay, so that is divided by C naught into G. Actually here it is G over G HL into 2, right? Yep, that's it. And since we have, I don't know if you can remember that instead of substituting 2 times, square root of G over G, if you multiply by G, square root of G over G is like multiplying by 1, and then this square root of G into square root of G is G, right? And that's divided by G over square root of G. So we can simply put it as square root of G. So I can represent this thing here as like that, AT over A. If you don't want to do this, you don't need to do it. Just substitute to this equation here. You're going to get the same answer exactly. Okay, so that is what we have for T. And what we need to calculate is the time required to drain from one height, and we want to know what is the second height. Okay, so it is going to drain from this height here. It's going to drain from that height, and what will be the height? How much is the amount that I'm going to lose? To know the amount that I'm going to lose, which is the mass in this case, right? I need to know the mass. And what is the mass? It is the density, which I already have, which is the area, which is I already have. All of what I need is to get the HL. Of course, what is HL? HL is the distance above that leak, right? Is the distance above that leak. If I know the distance above that leak, which is my new height, I will know the rest of that amount that had been leaked. And by knowing the rest of that amount, I can know what? I can know the amount that had been leaked. So all what I need is the information of HL. However, I have 2 HL, like it's like from one position to another. So what I'm looking for here is actually, it's like I have the time, delta T, right? I have the time, which is delta T. And what I need to do here is to find out how much time it really takes to go from one position to another. So if I want to put that, it's like I have a T1, right? And I have a T2 as well. So if I want to put this like as HL1, and then I'm going to put for HL2, and this is divided by C naught over G as well. And now if I want T1 minus T2, which is delta T, is equal to just taking a common factor, AT over A over C naught into square root of G, that is multiplied by a square root of 2HL1 that I already have, and minus 2 square root of HL2. So that is the time for it to go from one position to another. What is the time given to us? The emergency time that I have is 30 minutes, okay? And 30 minutes is equal to 1,800 seconds, okay? So I'm just going to write that here. So 30 minutes is equal to 1,800 seconds. So now, with this 1,800 seconds, is it good enough to calculate this or not, we are going to see. So let's substitute pi d square divided by 4 for the area of the tank divided by pi d of the whole, right, square divided by 4 divided by C naught. In this case, because I want to calculate the maximum flow, I just want to see how much I'm going to lose. So if I want to calculate the maximum flow, C naught is kept as 1 into square root of G. I'm dealing all with the feet, so it's 32.17 in this case, into 2 square root of HL1. And by the way, HL1, we know that it starts from 18 feet, okay, but we don't know what is the second time, like why did I put the 2 outside? So the 2 is inside here, 2 multiplied by 18, and that is 2 into HL2. So that is my problem, and I have actually all the information. I have also the information for DT and D4. If I can't recall now what's DT, but if you go back to the problem, okay, 6-inch diameter line, that was the diameter, and the diameter of the big thing here, it is 100 feet. Okay, it's 100 feet. So I'm talking about 6-inch, which is about 0.5 feet, right? So in this case, this will be, just to write these, this will be like 100 square, right? And this will be 0.5 feet square. So substituting all that, and to find HL2, I'm going to find that HL2 is equal to 16.5 feet, and that is the distance which is above, as I said before. So that is like this distance here, it is that distance here. So if I want to calculate the rest, is 18 minus that distance that I have obtained, which means if I want to calculate delta H, is 18 minus 16.5, which is 1.5 feet. Now that is the 1.5 feet. So what is the amount? The volume, which is pi d square of the tank, the diameter of the tank, over 4 into that delta H, which is that amount. It is going So imagine with that amount that you have 88,000 gallons spilled, how much does it cost? And if you think about the cost, you will say that this 30 minutes emergency plan is not accepted. We need to have some kind of another plan. So you just think about it, right? It's 30 minutes are really good. It's really good. But you are saying that this 30 minutes is not good enough for the amount of of what I'm going to lose. So sometimes it's good to do the calculation, because if you don't do the calculation, you cannot really imagine how much you're going to lose. Okay, great. So what else do we have? What else do we have from questions? I think so we have done pretty good number of questions here, and we will keep the third bit of solving questions